Hello, my name is Charles Champagne-Cosette, and in this video, I will present our work on localization using directional coordinates. To describe the problem we are studying, consider the goal of localizing some robot, such as a quadcopter, relative to an arbitrary landmark shown as the green pyramid. The goal is to estimate the 3D position vector of the quadcopter relative to a landmark using a combination of range, azimuth, or elevation measurements. As you can see from the equations on the right, the range, azimuth, elevation measurements are all nonlinear functions of the Cartesian x, y, z components. This requires the use of nonlinear state estimation techniques, which usually have suboptimal performance. Furthermore, if we replace the landmark by another mobile robot, and this almost identical problem now concerns the estimation of the relative position between the two robots. This is a prerequisite for many multi-robot tasks, such as collaborative inspection, mapping, and formation control. Our motivation for studying this problem comes from the fact that we are currently researching the relative position estimation problem in multi-robot teams using ultra-wideband radio. This consists of putting a UWB transceiver on each agent, which can at least be used to calculate the range between pairs of transceivers. There's been lots of previous work on similar problems. For example, the work by Chow proposes an algorithm to estimate the position of a robot that possesses a UWB transceiver relative to a single other static UWB transceiver called a tag. In our own previous work, we study a similar scenario, but with two mobile agents instead of one. Furthermore, there are recent methods that attempt to determine the angle of arrival of a UWB signal, which is effectively an azimuth measurement between the two transceivers. The work by Daltic and the Decawave team used two antennas on the same UWB board, whereas the work by Leder-Gerber look at the channel impulse response along with the deep learning approach to estimate the angle of arrival of the UWB signal. Let's now return to the original scenario where we are attempting to localize the blue quadcopter relative to the green landmark. At the beginning of an estimation task, we unfortunately don't know the true location of the robot, but rather only an uncertain initial guess of its location. This is called the prior distribution, and is usually assumed to be Gaussian. The gray dots are thousands of samples drawn from this prior, and hence represent a probabilistic visualization of the distribution of the robot's position at that point in time. An extended Kalman filter, which is one of the most popular state estimation algorithms, has no issue representing this distribution because it always assumes the state distribution is Gaussian. The red volume represents the 99.9% probability region reported by the EKF, and in this case, it perfectly represents the underlying distribution. If we then receive a distance measurement to the landmark, then the position distribution, now called the posterior distribution, changes significantly. It is now banana or spherical shaped, and the visualization you see here was computed with the particle filter, which we consider here to be the best representation of the true distribution. If we execute a Kalman filter correction step, we obtain the distribution shown by the red ellipsoid. Since the extended Kalman filter always assumes the state distribution is Gaussian, it can only generate ellipsoid-shaped distributions. This is a poor representation because the posterior distribution is most definitely not Gaussian. We can also further conclude that all Gaussian estimators, such as the EKF, the unscented Kalman filter, the Rauch-Tung-Streibel smoother, the least squares batch estimator, and others, will all ultimately fail to represent this posterior. Our approach is to reparameterize position by a new coordinate system, consisting of a range/distance, as well as the rotation matrix C. The rotation matrix rotates the unit direction vector along the x-axis to create a direction vector collinear to the position vector, whereas the distance scales the direction vector until it has the same length as the position vector. We show in the paper that it is straightforward to convert from Cartesian coordinates to directional coordinates and back, and we call the mapping from Cartesian to directional coordinates h. The mapping back to Cartesian position is the range times the rotation matrix times the unit direction vector along the x-axis. The goal is now to execute an extended Kalman filter, but in this new directional coordinate system. However, before we can do that, we must find a way to convert that initial prior distribution, which was expressed as a Gaussian and Cartesian coordinates, to some sort of equivalent distribution in directional coordinates. In our paper, we use sigma points for this step. We first begin by drawing Cartesian sigma points from the initial prior distribution. We then transform these sigma points to Cartesian coordinates by passing them through the mapping h. We finally use the converted sigma points to estimate an equivalent Gaussian distribution, but in directional coordinates. This creates the following We can visualize this by plotting a 99% probability region in directional coordinates, shown as the blue ellipsoid, and then passing that ellipsoid back through the inverse mapping to convert it back to the familiar Cartesian coordinates. This creates the following representation. As we can see, there is a slight mismatch between the true distribution and the one represented by directional coordinates, but overall, this is a pretty good fit, since the vast majority of points in the point cloud fall inside the region. In fact, this method performs well for a large variety of different Gaussian distributions in Cartesian coordinates. The 99% probability regions in directional coordinates, shown as the blue blobs, create some very interesting shapes when visualized in Cartesian coordinates. But most importantly, directional coordinates offer a significantly enhanced ability to represent this spherical or banana-shaped distribution that we saw earlier. The figure on the left visualizes the results from a single EKF correction step as the red volume, whereas the figure on the right shows the results from a single Kalman filter step as well, but in directional coordinates. We can quantify this fit by computing the divergence between the two filters' reported distributions and the point cloud itself. Over 10,000 Monte Carlo trials, we can see that the directional coordinates have a much lower divergence, indicating a much closer fit to the true distribution. We can also look at the Mahalanobis distance, which is a common consistency metric for probabilistic estimators. The lower the Mahalanobis distance, the more consistent the estimator, which is to say that the reported covariance does not underestimate the true covariance of the estimation error. We can then also run a Kalman filter in a dynamic scenario, where we also measure the acceleration of the robot, in which case we augment the state with velocity. We conducted 100 Monte Carlo trials where the trajectory is randomized in each trial by picking a random set of waypoints around the origin for the quadcopter to go through. Over the 100 Monte Carlo trials, we can see that the average norm of the estimation error is significantly smaller for the DCKF as opposed to the Cartesian EKF. Note that the actual magnitude of the error is somewhat meaningless, as it contains both position and velocity errors combined. The point of this graph is to highlight the difference between the two estimators. The difference is even more significant when looking at the average normalized estimation error squared, which is another common consistency metric. The lower Nice indicates a significantly more consistent estimator. We also conducted a brief experiment where we estimated the position of a handheld mobile UWB tag relative to a static UWB anchor on the wall. Although the difference between the Cartesian and directional Kalman filters is less dramatic in experiment, we still see benefits in both estimation performance as well as consistency. To summarize, we show that simply changing the coordinate system can have a large effect on estimation performance with the same underlying state estimation algorithm. Under high uncertainty, the proposed directional coordinate system offers a large improvement in estimation performance, especially so in consistency. If you have any questions at all, or simply want to get in touch, you can find my contact information on my website linked here. Thank you very much.